All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.
Do you know about longitudinal waves? What are they? Sound waves are properly known as longitudinal waves. But how would you define them? Hello everyone. I am Dr. Sachin Kumar. Welcome to S. Chand Academy. And today we are going to discuss about longitudinal waves. If you want to study this topic in detail and some other topics of engineering physics, you can refer this book of S. Chand Publishing. You can also find their ebook link in the description box. So basically, longitudinal waves were a mystery at its time when there was nobody who was able to solve its equation. Basically, it is not easy to define something which is not physically visible to you, something moving in space. In case of longitudinal wave, how would you define them? At the very first place, you can say that the sound is longitudinal waves. When I am speaking to you, my throat muscles are vibrating, and because of that vibration, some layers of the air, they are also vibrating. They are transferring this vibration to the other layers, and in this way the sound is traveling. Basically, if you look at, so in the direction of propagation, your particles of air move. If the sound wave is moving in a particular direction, so only in that direction these molecules of air, they oscillate like this. That's why we call them longitudinal waves, in which the direction of oscillation is same as the direction of propagation of energy. Now let's discuss how can we derive its equation. In this case, this could be a very difficult expression, but we will make it quite easy. So just 3 steps. If we learn these 3 steps, then you will find that this expression is one of the easiest one. So what are those 3 steps? When I am speaking something to you, in that case, first of all, in the step 1, what is happening? The gas is moving. When our throat muscles are vibrating, that vibration is transferred to the air. Now the air moves, and we can find that there is a change in its density very locally. So at a very small scale, you will find that at some place the density is higher and at some place the density is lower. And this compression and rarefaction, these are basically, they define longitudinal waves. So first step, when gas moves, it changes the density. After that, we can say that okay, when the density changes, it generates the change in the pressure. So in this air, at different levels, you will find different level of pressure. So when the density at certain place changes, you can just imagine, like if you open a bottle of perfume at some place, so vapor pressure is higher at that place, and those vapors, they transmit to other places because there is a difference of pressure. So when at the place where the density is higher, from that place you will find that gas molecules will move towards the place where density is lower. So in this way, so you can say that a pressure difference will generate. And in the third step, we can understand that okay, when there is a pressure difference, this pressure difference will cause a force which will make this gas to move again. So overall, so when gas is moving, this is creating change in density, and when there is a change in density, this is causing a change in pressure. So when there is a variation in pressure, this is causing a force which is allowing the gas to pass or the gas to flow. So in this way, a sound wave travels overall. So let us discuss this mathematically. Let us consider a volume, a block of air. So we are considering a block of air in this case, and we are imagining, okay, this block is starting from this point x and going up to this point x plus delta x. And we can also imagine, we can define some quantities for this region. Let us consider its density is rho naught. So this is the very beginning state, the state when there is no sound in this environment. Now just because of some sound, this air, this block of air will displace, and we imagine that this block of air will displace to and will make another block of air like this, and we can define one of its end to be x plus chi x. So this chi is somewhat a function of this x only. This is overall defining the change in the position of this block because of that sound. The other part, the other end of this air block x plus delta x will move to this point x plus delta x, and plus, because at this point chi will also work like x plus delta x. So this can also be defined like this. So this is a new block because of our sound. This block, the earlier block of density rho naught, is now of density rho. So in this way we can define these two blocks, one without sound and one after the sound. It is newly created because of that sound. At the beginning, the mass of the block is rho naught into delta x, and after this block being influenced by the sound, we will find that its mass will be rho into, so just to find its length, we can do one thing, we can just subtract from final quantity minus initial quantity, we can just do that, and we will find that, okay, x plus delta x plus chi, which is a function of x plus delta x, and minus, we can subtract x and this chi x, which is the initial point. Now if you look at this expression, you will find that this x can be cancelled from both sides. This is now a simplified expression. We have gathered rho naught delta x is equal to rho, and here I am rearranging these quantities like chi x plus delta x minus chi x, and overall I have plus this quantity delta x like this. Now if you look at this quantity chi x plus delta x minus chi x, so you can define some differentiation out of this definition. So if you just divide this quantity by delta x and multiply it with delta x, in that case you will find that, okay, if delta x is small, that is obviously very small in the case of longitudinal waves, when the transformation of energy from at one place to another place, or the wavelength of your longitudinal wave is quite small, in that case we can change this definition to a differential, and overall we are writing here, so this is rho naught delta x is equal to rho, and here the definition is d chi by dx delta x plus delta x. Now in this definition as well, delta x can be taken out and can be cancelled from both sides. Overall you will get rho naught is equal to rho d chi by dx plus 1. So this is a modified definition. in which this chi, which is a function of x, is influenced by the space parameter x and plus 1 that quantity, as we know that okay, the density because of sound is modified, and you can see that okay, this rho, the new density, is equal to the rho naught, the old density, and rho e, which we can define as the change in the density because of the sound. If I put this definition of rho at this place, then by simply rearranging some of the quantities, we will get an expression like this, which is rho e is equal to negative of rho naught del chi by d chi by dx. As we know, the mass of the system will not change before the sound and after the sound, and overall this is the mass per unit area overall, and rho naught delta x we have defined. And in the second term we can see that okay, chi x plus delta x minus chi x divided by delta x, so this can be defined as a derivative. But we know that this function chi is also a function of time. So this variation in the air because of sound is also varying with the time. In space there is variation, and in time there is also a variation. So that's why when we are writing it, rho naught delta x is equal to rho, so we are writing it as del chi by del x, delta x plus delta x, like this. So overall you can see that okay, we can take this delta x out, and we can cancel it from the both sides, and the equation we get like this: rho naught is equal to rho del chi by del x plus 1. So yes, this is the equation we are getting. Now we can just understand about this density. We can redefine this in a certain way, like this density rho is equal to rho naught, which is the density of the air at the very first place, plus rho e. Rho e is the variation, the small variation in the density of the air because of sound. So we are writing it as rho naught plus rho e. Now if I insert this definition of rho into this equation and rearrange some parameter, so overall I will get rho e, just because I want to calculate that what is the variation in the density. So I am writing this equation in terms of rho e. So rho e is equal to negative of rho naught del chi by del x and negative of rho e del chi by del x. So this is the new equation we have written at this place. Now we know that okay, the change in density rho e is very small quantity, and also this quantity del chi by del x is also a very small quantity, and overall the product of these two quantities will also be very small. So in comparison to the second quantity, so this quantity can be neglected. Overall, what we get out of this equation, we get that rho e will be equal to negative of rho naught del chi by del x. Yes, this is the equation. This is the very first equation. Overall we defined that okay, when gas moves, so it changes the density of the air. So defining that term, this is the first equation which is going to help us in defining the longitudinal waves and their equations. Now there is one more thing, that this change in density will cause change in pressure. But how would we define that? So how this change in density can define the change in pressure? This is the next question that we are going to answer after a short break.
Hi, I'm Manisha Singla. इनऑर्गेनिक और ऑर्गेनिक के कुछ डिफ़िकल्ट कॉन्सेप्ट्स को आसानी से समझाने के लिए मैं आ रही हूँ एस चांद अकेडमी में। तो अगर आप हमारे वीडियोस को देखना चाहते हैं तो सब्सक्राइब ज़रूर कीजिए।
Welcome back to S Chand Academy. Before going to break, we were discussing about the longitudinal waves, and we had already discussed about how the motion in the gas changes its density. Now the next question is how the change in the density can cause a change in pressure. So let's look at it, how the change in density is causing a change in pressure. First of all, we should know any relation about them, how they are related. The pressure is P node plus PE. This can be defined like this, where P node is the pressure at very first place and this quantity PE is the change in the pressure. And on the other hand, we have already defined the density like this, which is rho is equal to rho naught plus rho E, where rho naught is the density at very first place when there is no sound and rho E is the change in the density. Now what is the relation between them? Only using this relation we can derive an expression, and we can use that expression to simplify or to derive the equation for longitudinal waves. But in this case, you will happy to know that this quantity change in pressure is directly proportional to this quantity rho E, which is a change in density. So how much you vary the density in this air, proportionally the same amount of pressure will change. That's very nice. So they are proportional and you can easily understand them. So PE is equal to this quantity kappa rho E. So this quantity kappa overall is a constant, and we can understand that this is a property of the gas or the medium in which this sound is traveling or this sound is moving. So in this way this equation can be defined. We can name this as equation number 2, just because we said that okay, number 1, when gas moves density varies, number 2, the change in the density causes a change in pressure, and this equation number 2 defines that property only. So the change in pressure is equal to kappa, the change in density. So let's record this as equation number 2 and let's move to the equation number 3 we are going to derive. In the third point, we were discussing that when there is a pressure inequality in the medium, so consider that there, at this place we have higher pressure and at this place we have lower pressure. So overall, because of this inequality, the gas will move from higher to lower pressure. So in this way the sound wave will travel in this air. Now if I want to write this mathematically, so there should be at least some force. This force only can drag this air and make this wave move. So in this case we can derive an expression where we can see the variation in the pressure and also the force per unit area. How much force per unit area is developed because of the change in that pressure. So at this place, if I write this, I can write this as rho naught delta x, which is the mass per unit area. So we are just taking it as a sheet of unit area, and we are imagining that okay, through this sheet we are imagining this quantity delta x. Now rho naught delta x, which is the mass per unit area of this air block, into, if I want to define acceleration at this place, so I can write that second derivative of del chi by del x square. So overall this is mass into acceleration divided by area. So first quantity rho naught delta x is mass per unit area, and the second quantity is a representation of the acceleration in the air because of the change in pressure. But where is the change in pressure? So overall there should be some force that is causing this air move. Now if I write this, I can write this as rho naught delta x, which is a mass per unit area. So we are imagining a sheet of unit area, and through this we are imagining a block of length delta x. So rho naught delta x into del square chi by del t square. So overall you can see that this is the first portion is mass per unit area, and second portion is representing you the acceleration in the air. Overall this is force per unit area, which is equivalent to the change in pressure. So on the other side of the equation you should have the quantity like change in pressure. So what is the change in pressure in this case? If I write this, so we have the length of the box to be delta x, this block is delta x width, then this can be written as negative of del p by del x into delta x. So this is the change in pressure. Why this is negative? Just because the force applied is in opposite direction to the pressure gradient. That's why we have a negative sign here. Now in this expression, this quantity P can be substituted by P naught plus PE, and we know that this quantity P naught is just a constant because it is the constant of the medium which we have taken at very first place. So its derivative will give you a 0. Only this quantity PE will be there. So overall this equation will be written as rho naught delta x. This delta x can be cancelled at both sides, so I need not to write this delta x, and rho naught del square chi by del t square is equal to negative of del PE, which is the change in pressure, by del x. Yes, so this is the equation. Now this is our third equation, in which we know that there is one force quantity, and that force quantity is because of the change in pressure in the air in the medium. Now using these three equations we can derive the equation of motion, in this case of longitudinal waves. So let's do this. Let's first pick this equation number 3. In this equation number 3, where we have written this quantity PE, then how can I replace this quantity PE in terms of rho E, which is the change in the density in the medium? So we know that this quantity PE is equal to kappa of rho E. So I can just write it in at this place, rho naught second derivative of chi with respect to time, negative of kappa del rho E divided by del x. Yes, so using equation 2, when we modify equation 3, we get quantity like this. So this is minus kappa del rho E by del x. Yes, so this is the new modified equation. Now but this is not the wave equation, because there are certain quantities which we don't know. We want this equation in the terms of chi. So what if I use the first equation at this place? So if I use first equation, so in that equation we know that this quantity rho E can be substituted in terms of del chi by del x with rho naught and minus sign in multiplication. In that case, if I write it like this, we know that this equation will be in this form, where the rho naught on the left hand side and right hand side will be cancelled, and we will get equation like this. Second derivative of chi with respect to time is equal to this quantity kappa there is already a negative sign and one more negative sign will come, so they will cancel out, make it a plus sign, and overall when we substitute rho e using first equation, we will get the second derivative of chi with respect to x. Overall, you are getting this equation in which at left hand side you are getting the second derivative of chi, and on the right hand side you are getting the second derivative of chi with respect to x with this quantity kappa. Now, if you look at it carefully, this is approximately the same expression, or you can say the similar expression like the transverse wave we have already studied in our previous lectures. The same variation with respect to time and same variation with respect to x. And in that we also studied the velocity of transverse wave, and in that case as well we know that this quantity kappa should be equal to v square. V is the velocity of the sound in that medium. So overall this v will be equal to square root of this quantity kappa. This quantity kappa is a property of medium, and only on its property the velocity of sound in that particular medium depends. In this way, overall you can understand the longitudinal waves in 3 steps, and in each step you can derive a mathematical expression, and at the end you can combine them and make one equation. So if we look at this lecture as a whole, we will find that initially we started with the definition of longitudinal waves, and we defined 3 basic concepts through which this longitudinal wave can be defined. Using these 3 concepts, we derived 3 mathematical expressions, and one after another we derived them using simple mathematics, and at the end in the third equation we inserted the values we obtained from equation second and equation first. We just inserted their values and we derived the equation of motion for longitudinal waves. So the equation looked similar to the equation we have already obtained for transverse waves as well. In that case, we can also define the velocity of that wave in a particular medium using the constant kappa, which is a property of the material. If you want to study this topic in detail and some other topics of engineering physics, you can refer this book of S. Chand Publishing. You can also find their ebook link in the description box. Please like this video, please share this with your friends, and don't forget to press the bell icon. You can also comment us which topics you want to study in this subject or the related subjects of physics. Take care and have a very good day.